Okay, students, now we'll start with the digital communication system. Now in the digital communication system, the first step, which is nothing but now you want to first convert that analog signal into a sequence of binary ones and zeros. So while in the process of converting analog signal, a continuous wave signal, into a sequence of binary ones and zeros, the first block, the first step is nothing but sampling. You want to sample the signal. So what is sampling? Now how the signal is sampling and all these things we'll see, but before that we'll see what the sampling theorem is saying. Now what the sampling theorem is saying is a signal, a message signal. This is a message signal. A message signal band limited to, this is a message signal band limited to omega h. I mean, say message signal which is having a bandwidth of omega. A message signal band limited to, this message signal is band limited to omega hertz. This message signal which is band limited to omega hertz. This message signal which is band limited to omega hertz can be reconstructed back from its samples. A message signal band limited to omega hertz, note down this definition of sampling theorem. A message signal band limited to omega hertz can be reconstructed back from its samples only when the sampling rate which is greater than 2 omega samples per second. This is the sampling theorem says. A signal band limited to omega hertz can be reconstructed back from its samples only when the sampling rate is greater than 2 omega samples per second. This is the definition of sampling theorem. Now we'll see how a signal is converted to samples and how the samples are again get back the original message signal. So we'll see both. Okay. Now this is a message signal which is a continuous wave signal, continuous in amplitude and continuous in time signal. Continuous in amplitude and continuous in time signal. Now this continuous in amplitude and continuous time signal now multiplied with an impulse train. This is the train of impulses. Now this is a continuous in amplitude and continuous time signal. Now is multiplied with an impulse train. Is multiplied with an impulse train, then it will be converted into now the time is discontinuous or not? Now this is discontinuous in time, and this sample strength and this original message signal strength is same. This sample amplitude and this original message signal amplitude will be same. Now discretizing in time, and all these amplitudes will be same. Let us take for example. Now at 0 seconds, this amplitude is 0.5 volts. Now at 0 seconds, this sample amplitude is also 0.5 volts. Therefore, this is a continuous in time. Now the discretizing in time is called as sampling. This is called as sampled signal. What is sampling? Discontinuous. Discretizing in time is called as discretizing in time is called as sampling. Discontinuous in time is called as sampling. So now here the time is discontinuous. Now these amplitudes will follow the same amplitude of the message signal. Therefore, this is called as continuous in amplitude. We may call it as continuous in amplitude, and all times are discontinuous, and this is a sampled signal. Let us take this is a sampled signal. This is the sampled signal. Now the time is discontinuous. So now this is one step which is completed, where continuous wave signal, analog signal, is converted into samples. A continuous wave signal, analog signal multiplied with a train of impulses. Now this is called as sampled signal. Discretizing in time is called as sampling. Therefore, how you can get the sampled signal? Now this is the sampled signal, m delta of nts. This is the sampled signal, which is nothing but now the message signal multiplied with a train of impulses summation n equal to minus infinity to infinity, summation n equal to minus infinity to infinity delta of t minus nts. Now this is the impulse train, right? Now this is the train of impulses summation n equal to minus infinity to infinity delta of t minus nts. Now this is a train of impulses multiplied with a continuous wave signal. Now you can get the sampled signal. Now where ts, now see here the successive time difference between each sample is ts seconds. The successive time difference between each sample is ts seconds. Therefore, now this ts seconds is called as, now this is the sample signal where ts seconds is called as sampling interval. Sampling interval or sampling time, where ts is sampling interval, sampling time, where 1 by ts is sampling rate, where 1 by ts is sampling rate, which is samples per second. This is the sampling rate. Now sampling rate, now fs, which is nothing but sampling frequency. This is the sampling frequency. Now this is the sampling rate. Now sampling frequency, which we call it as hertz, sampling rate, which is called as samples per second. Let us take 30 kilohertz is the sampling frequency, which is nothing but 30 kilo samples per second is the sampling rate. This is the sampling rate and this is the sampling frequency. Okay, note on this. Now this is the way a continuous wave signal is converted to samples. So now in the same manner, what we are doing is, now we want to get back the continuous wave signal from its samples. So what should we do is, now I want, this is the sample signal, these are the samples. So from these sample signals I want this. Now what we are doing in the first step, m of t we are converting into sample signal. Now in the second step, now these sample signal to these sample signals to continuous, I want this. Okay. So such that now the reverse process is also completed. From samples you want a message signal. So the same manner I can do in a frequency domain. So can I do like this? M delta of NFS. Now this is the sample signal in frequency domain to m of f. I want to show this such that it is easy for us. Okay. So sample signal, this is the sample signal in frequency domain to message signal in frequency domain. Sample signal in frequency domain to message signal in frequency domain. So I want to show this. So for such that we want to apply Fourier transform. Fourier transform of m delta of n ts, which is equal to Fourier transform of m of t. Now this is multiplication in time domain, convolution in frequency domain, Fourier transform of summation n equal to minus infinity to infinity delta of t minus nts. So Fourier transform of m delta of nts, which is nothing but capital M of nfs, capital M of nfs, which is equal to Fourier transform of m of t is m of f convolved with Fourier transform of this is 1 by ts, or this is summation delta of f minus n into fs and multiplying or scaling of delta of t minus at, which is nothing but 1 by a into delta of f minus. So which is nothing but, now this is fs summation n equal to minus infinity to plus infinity m of f convolved with delta of f minus nfs. Now this is m delta of nfs. Now which is nothing but the sample signal in frequency domain, which is nothing but fs summation n equal to minus infinity to plus infinity m of f minus n into fs. Now this is the sample signal in frequency domain, m delta of nfs, which is nothing but 1 by ts summation n equal to minus infinity to infinity m of f minus n by ts. This is the sample signal in frequency domain. Now our sample signal, this is in time domain, now that is in frequency domain. Sample signal spectrum. Now we will see this sample signal in frequency domain, and after that we will get the original message signal or not. Hold on. Now we'll see the sample signal in frequency domain. M delta of NFS, which is equal to 1 by Ts summation 1 by Ts summation n equal to minus infinity to plus infinity m of f minus n into, this is the sample signal in frequency domain. Now we'll see, this is a sample signal. Now whose Fourier transform is? Now this is a sample signal whose Fourier transform is? Now when n equal to 0, now this is m of f. Now when n equal to 1, then this is n equal to 1. Now this is a signal which is at 1 by Ts. And so on. When n equal to minus 1, now this is minus 1 by Ts minus 1 by Ts plus omega minus 1 by Ts minus omega. Now this signal strength which is multiplied with, this is k, therefore this is k by Ts. Now see here, this is the sample signal. This is the sample signal in frequency domain. This is the sample signal, spectrum of sample signal, right? Spectrum of sample signal. Now this is the spectrum of the sample signal. Spectrum of the sample signal. Now what is this gap? This is the spectral gap. How much it is? This is 1 by Ts minus omega which is greater than 0. Therefore this is 1 by Ts minus 2 omega greater than 0. Therefore 1 by Ts greater than 2 omega samples per second. Now if the sampling rate which is greater than 2 omega samples per second, now your sample signal in frequency domain is like this, which means that if you are transmitting these samples as many as you can, as many means which is greater than 2 omega samples per second. Let us take one small example. Here omega is 10 kilohertz. If this omega is 10 kilohertz, how many samples you need to transmit? Now this sampling rate which is greater than 2 into omega, 2 into 10 kilo. Now which is nothing but this sampling rate which is greater than 20,000 samples are transmitted per second. If you are transmitting greater than 20,000 samples per second, now your spectrum will be appear like this with a spectral gap or a Gauss band of this much. This is a spectral gap or a Gauss band. Now what is the advantage? Now the advantage is the reconstruction is possible with the help of practical low pass filter. This is your low frequency information signal. Therefore this is the practical low pass filters are useful because that will be enter into the transition bands, enter into the spectral gap. So you can get back your original message signal. Now you can get back your original message signal in frequency domain from the sample signal you can get back your original message signal. This is M of F. Now see here, don't confuse. This is sample signal in frequency domain. This is a sample signal in time domain. These are the time domain samples. If you are transmitted greater than 20,000, your spectrum will be appears in frequency domain like this. But here I don't want all these things. I want a message signal which is a low frequency information, low pass filter. Now this low pass filter is also called as reconstructed filter. This is the reconstruction filter. Is nothing but a low pass filter. Therefore, once this kind of samples are available, now you can get back your original message signal just by using a reconstruction filter or a low pass filter. Now, if you want in time domain, then inverse Fourier transform, then you can get your original message signal, which is a continuous wave signal in which domain? Time domain. Now, this type of sampling, this is the case 1. This is case 1. Now, what is this case 1? Now, the case 1, which is called as oversampling. Which sampling? This is called as oversampling when a sampling rate, this is the oversampling when a sampling rate which is greater than 2 omega samples per second. Now, you always done the signal is to be sampled which is greater than 2 omega samples per second. This type of sampling is called as oversampling. Now, the advantage of the oversampling is now the reconstruction is possible with the help of practical filters. Of course, the disadvantage is bandwidth is increases. Not a problem. And there is a spectral gap. What is this spectral gap? This is the Gauge band or spectral gap. Gauge band or spectral gap of how much? The Gauge band or a spectral gap of Fs minus 2 omega hertz. This is a spectral gap or a Gauge band such that then the reconstruction which is very easy. The disadvantage of this oversampling is bandwidth is increases. Advantages is reconstruction is possible with the help of practical filters. Okay. So in the digital communication, you always do the signal sampling which is a rate of greater than 2 omega samples per second. Okay. Note down. Okay. Now we are doing a signal sample with a rate of 2 omega samples per second. Now we are doing the signal sampling which is exactly equal to this much of rate. Now the signal sampling which is exactly equal. Now this is 1 by Ts. Minus 1 by Ts. Now what is this gap? Here there are two signals. Now this upper limit is omega. This lower limit is 1 by Ts minus omega. Now what is this gap? 1 by Ts minus omega. Now this gap which is equal to 0. Now this is equal to 0. Therefore, which is equal to 2 omega samples per second. Therefore, sampling rate is exactly 2 omega samples per second. Now such kind of samples are only 20,000 you are transmitting exactly. Now your spectrum appears like this. Now in such a cases, then the filter designing is very, very difficult for us. Such a cases, now this is the low pass filter, is difficult to reconstruct it back. Or M of T. Because now these are the transition band which is equal to 0. Now if the transition band is 0, these filters are very, very close to the ideal filters. Therefore this is called as ideal sampling. This is called as ideal sampling. This is ideal sampling. Now when the sampling rate which is equal to 2 omega samples per second, the ideal sampling when the sampling rate which is equal to 2 omega samples per second. Now this is the sampling rate which is equal to 2 omega samples per second. Now with a Gauss band or a spectral gap. What is the spectral gap? Spectral gap of 0 hertz. No, there is a spectral gap of only 0. Now this is the spectrum of the sample signal. When the sampling rate is exactly equal to 2 omega samples per second, it is somewhat difficult, and the filter which is very close to the ideal filter. Okay. Now this is the ideal sampling. Now this is the minimum sampling rate. This is the minimum sampling rate. So the minimum greater than 2 omega, which is good, but this is the minimum sampling rate. The minimum sampling rate is also called as minimum sampling rate is also called as the minimum sampling rate is also called as Nyquist rate. The minimum sampling rate is called as Nyquist rate. Therefore, if nothing is given, the sampling rate which is equal to Nyquist rate. The sampling rate which is equal to the Nyquist rate. So if you are designing an ideal filter or a practical filter with a zero transition band, in such a situation, we can get back this original message signal. This is M of F. Now this is the inverse Fourier transform. Now if you apply inverse Fourier transform, now this is the message signal. But this is the minimum. If you greater than this, the sampling rate is greater than the Nyquist rate, which is good. The sampling rate which is greater than the Nyquist rate, then practical filters transition band is also not a problem. But if the sampling rate which is exactly equal to the minimum rate which is called as Nyquist rate, then the problem with the designing of filter reconstruction is somewhat difficult. But advantage is now Gauss band is 0, spectral gap is 0, therefore bandwidth is decreased. Okay, so advantage here is bandwidth is less, but disadvantage here is design of filter with 0 transition band. Now, if the sampling rate is if the sampling rate is less than 2 omega samples per second. What happened now? If the sampling rate, which is less than 2 omega samples per second, spectrum of the sampled signal. When the sampling rate, now 1 by t is minus omega is less than 0. Now 1 by t is minus 2 omega is less than 0. 1 by t is less than 2 omega samples per second. Now when the sampled signal, when a sample signal is less than 2 omega samples per second, when the sampling rate is less than 2 omega samples per second, the problem is that then this is adjacent channel interference and this is the overlapping of the signals, and this reconstruction will not possible. Now this effect is called as aliasing effect. This effect is called as aliasing effect. Now therefore never do the signal sampled with a rate of less than 2 omega samples per second. Always the signal is to be sampled which is greater than or equal to 2 omega samples per second. It is better for oversampling, and in a rare case ideal sampling, which is nothing but which is equal to the Nyquist rate. But never do the signal sampled which is less than 2 omega samples per second, which is undesirable and aliasing the effect, and your information definitely lost. Okay, note on this. Oh, sorry. This sampling is called as undersampling. This is called as undersampling. This is undersampling. The signal sampling rate is less than 2 omega samples per second is undersampling. Don't do the undersampling. Always better go for oversampling, or in a worst case a critical sampling or ideal sampling or Nyquist sampling, and this is undersampling. Don't do that. Okay. Now, if m of t, which is equal to 10 plus 10 cos 200 pi t, this is the message signal. Now, and it is sampled at a sampling rate of 500 samples per second. A sample with a sampling rate of 500 samples per second. He is asking verify aliasing effect. First question is verify aliasing effect. Second question is spectral gap. and third bit is draw the spectrum of the sample signal. Draw the spectrum of the sample signal and what is the cutoff frequency of the reconstructed filter. Okay, I'll explain one by one, not a problem. Okay. Now first we will verify aliasing effect. Now if you want to verify aliasing effect, now what is m of t? M of t, which is equal to 10 plus 10 cos 2 pi into 100 into t. Now the frequency of the message signal, which is 100 Hz. Now the Nyquist rate, which is equal to the minimum sampling rate, which is equal to 2 into 100, which is equal to 200 samples per second. 200 samples per second is the Nyquist rate. But minimum rate is 200 samples per second. But what is the sampling rate? The given signal is sampled at, the sampling rate is 500 samples per second. Now what is here? The sampling rate which is greater than the Nyquist rate. Am I right now? Now the sampling rate is 500, Nyquist rate is only 200. Therefore the sampling rate which is greater than the Nyquist rate, therefore which is an advantage, there is no aliasing effect. There is no aliasing effect. Question number 1. There is no aliasing effect because signal sampling rate is greater than the Nyquist rate. Now there is no aliasing effect. Now spectral gap. You know that now when there is no aliasing effect, here we understand this is which sampling? Oversampling. Because sampling rate which is greater than the Nyquist rate, this is oversampling. When oversampling is the signal is oversampling. Now what is the spectral gap? The spectral gap or a Gauge band, which is nothing but Fs minus 2 omega hertz. Now what is Fs? Fs, which is nothing but 500 minus 2 into omega is nothing but 100. So which is nothing but 500 minus 200. Now the spectral gap, which is equal to 300 Hz. Spectral gap or a Gauge band of 300 Hz. Now m of t, which is equal to 10 plus 10 into cos 200 pi t. Therefore m of t, which is equal to 10 plus 10 cos 2 pi into 100 into t. Therefore what is m of f? M of f, which is equal to 10 into delta of f plus 10 by 2, which is nothing but 5 into delta of f minus 100 plus delta of f plus 100. Now this is the spectrum of message signal. Now what is this? This is nothing but spectrum of message signal. Now at 0 this is 10. Now at 100 at minus 100. Now this is 5. This is the spectrum of the sample signal. Okay. Now see here what he is asking. Now what is the spectrum of the sample signal? Now here is the spectrum of the sample signal which is available here. Now I'll write. Now this is nothing but 500 summation n equal to minus infinity to plus infinity m of f minus 500 into n. Now which is nothing but now when n equal to 0, now this is m of f. Now this is minus 100. Now this is 500 into 5000. This is 2500. Now, when n equal to 1, m of f minus 500. When m of f minus 500, now this 0 is at 500. Now this 100 is at 600. This minus 100 is at 400. Now this is shifted to 500. And so on. Now similarly, when n equal to minus 1, now this is at minus 500, this is minus 600, this is minus 400. Now, see here, this is the spectrum of the sample signal. Now, what is a low pass filter? Now, to get back this original message signal, now this is the message signal. Now, what is the cutoff frequency of the filter? The cutoff frequency, now you are designing a low pass filter to selection for this. Now, this is the low pass filter or reconstruction filter for selecting this signal, and with a cutoff frequency of 100 hertz. With a cutoff frequency of 100 hertz. Okay, there are questions. No aliasing effect, spectral gap or God band, because oversampling, definitely there is a God band. And this is the spectrum of the message signal. This is the spectrum of the sample signal. And to get back your original message signal, the cutoff frequency of the low pass filter will be 100 hertz. Okay, now this is one example such that you can understand the sampling theory. Okay, now done.